All right, so 7.6, properties of logarithms. Our goal is to at least do half of the notes today and probably finish the other half tomorrow. It's just I don't want to rush them. So basically, we want to understand that logarithms and exponents have corresponding properties. So what I can do with a log and what I can do with exponent, they work together. And that's because if you did your do now, the relationship between a log and an exponent with the same base is that they are inverse functions, right? So hopefully you got that correct. All right, we're going to start here with definition of a log. So the logarithm log base bm is the exponent to which b must be raised to get m. Okay, that's what the log is asking you. What would the power of b have to be in order to get the value of m? So we have three types of logs. We have our log with any base. So if I have log with any base, as you can see here, if it's written as log base b x equals y, to rewrite it in terms of an exponent, it becomes x equals b to the y. And there are restrictions for b. B has to be greater than 0, b cannot equal 1, and x has to be greater than 0. Okay? Natural log. So natural log is where we're working with ln and e. So natural log of x equals y. If I want to write it as an exponent, it becomes x equals e to the y. And again, x is greater than 0. Common log is when our base is 10. So for common log, we do not actually write a base. It's b equals 10 is implied. And then with that, what that means is that to write the exponent, it's x equals 10 to what power? 10 to the y. And again, x has to be greater than 0. All right, so let's apply some of these. So here we're going to go from log to exponential form. The first thing I'm going to do is identify what I have. I have my b, which is 4. I have my x, which is 16. And I have my y, which is 2. The rule tells me that if I want to write it as an exponent, it becomes x equals b to the y. So I'm going to plug in what I have. What is my x? 16. What is my b? 4. What is my y? 2. Is that a true statement? Does 16 equal 4 squared? Yes. All right, so I want to stir it off so that you can see how and why it works. Now, there's going to be variables and unknowns. So here I have log base b, 7 equals 5. So I have my b, my x, my y. And again, to write an exponential, I'm doing x equals b to the y. So my x is 7, my b is b, and my y is 5. So something to the 5th power equals 7. All right. Natural log, remember the inverse of the natural log is using e. So its rule is x equals e to the y. Okay. My variables that I have are just simply x and y. So this case is c equals e to the 3.
So you're only going to have a b when you have log?
Mm-hmm. Natural log, it's b is e. If you didn't do your notes last week, you may want to jump on that bandwagon. All right, how do we feel about going from log to exponential? All right, so now we're going to go from exponential to log. So we're going to go the other way. So here, labeling what I have, I have my b, I have my y, I have my x. I have my base to the y and my x. And so this time I want to write as a log. So log base b, x equals y. So log of 2 my x is 1a equals -3. Okay. On 5, on the common log, the reason why it's the common log is because my base is 10. So I have my b, my y, my x. When it's the common log, you actually don't have a b to write. It's just log x equals y. So I have log, my x is 1, my y is 0. Okay. Next, we have an example with natural log. I know it's natural log because there is an e. So for natural log, it's just natural log x equals y. So here's my y, here's my x. That leads me to the natural log of 12 equals a. So we did an example of b being anything other than 10. We did our common log, and we did our natural log. The key thing is knowing where the variables are. All right, questions, comments, concerns? Okay, we're going to go into our properties. So we're going to start off with our log properties. So we're going to be simplifying logarithm expressions. We're going to start with our first property. Our first property is when you have a log to the base of the log. And what happens is they are inverses of each other. They're going to end up canceling one another out. So when I have b to the log b, they're going to end up canceling each other out. And all I'm left with is whatever the value is that's left standing. Okay? And then property 2 is saying the same thing. If I have a log b and my x value here is b as well, they're going to cancel each other out. That's because they're inverse operations. It's like multiplying a fraction by its reciprocal. It turns the value into 1. Okay? And so these are pretty straightforward, pretty simple. So here, this is property 1. So using property 1, I have a power base of 5, a log base of 5. They cancel each other out. The answer is 18. Do you see that? Okay, using property 2, I have a log base of 3, a power base of 3. They're going to cancel each other out. And I'm just left with x minus 2. Okay, this rule also applies when it's natural log. So just like you're using the inverse of the log in its base, natural log and e are inverses of each other. So when you have the natural log of e, it's going to cancel out, and I'm just left with 3t. If I have e raised to the natural log, same thing, same effect. I'm going to cancel it out. I'm going to left with t squared. So this is just a variation of property 2, and this is a variation of property 1. All right, how do we feel? Doable? Okay, so that's property 1 and property 2. So for the next properties, 3, 4, and 5, we're using the same logic of laws of exponents. So with our laws of exponents, remember, if I am multiplying with the same base, that means I'm adding their powers, right? If I'm dividing with the same base, that means I am subtracting those powers. The same rules that apply to those laws of exponents are going to apply to our log properties, okay? So property 3, this is our product rule. My pen just stopped. There we go. So property 3 is our product rule. If I have a log base b with the x's being multiplied, m times n, they can be separated into log base m plus log base n. So looking at example 5, I can expand this. So expanding it means that I'm going to end up with 2 logs. So expanding, I have log base 4 of 5 plus log base 4 of x. Expansion is good when there is a variable and you're trying to separate the constant from the variable. So notice how here I separated my constant from my variable. Okay, questions on expanding? All right, condensing. So condensing is I'm making it smaller. So seeing how that this is addition with the same base, to condense, instead of making it addition, I'm going to make it back into multiplication. So when I condense, it's log base 2, and I end up with 6 times 10, which equals log base 2, 60. So what this is asking me, 2 to the what power equals 60. But this is condensing. Okay, expanding, I want everyone to have their own log. Condensing, I want it written as few amount of logs as possible. How do we fill out property 3? Okay. Property 4 is our quotient. Okay. Quotient. And remember, quotient is division, right? So if I'm dividing, I can expand it to subtraction. If I'm subtracting, I can condense it to one single division. Okay. So to expand the natural log here, because the same rules apply to log and natural log, is that if I have natural log of 6 over x, it can be expanded to the natural log of 6 minus the natural log of x.
That's different on our paper.
I think I actually changed it on y'all's log so that it would match. Didn't I? I did. I can go back and edit. But guess what? It doesn't make a difference. Because it's still the same thing. All right. How do we fill out expanding with quotient rule? Okay, condensing. So again, condensing means that I want to go from 2 separate logs down to 1. I look at my operation. My operation is subtraction. So in order to condense, it means I'm going to divide. So we have common log. Why is it common log? Because I do not have any other base. Common log of 50 divided by 25. I'm going to keep simplifying that. What is 50 divided by 25? 2. So common log of 2. All right. Oh, this is going a lot faster than I thought. We're gonna keep going. We can do this in one day. All right. Property 5. So property 5 is our power rule of exponents. So power, and it applies to multiplication. So this is a little different. This is our power constant. The power of a log can also be the constant of the log. So the power can become the constant. So here we have k times log base m. And what this is good for, again, if you're trying to get the variable by itself. So here we have log x to the third. And to expand, I'm going to take the power and make it into the constant. So this just becomes 3 log x.
See, all of this seems pretty simple now, but in a few moments when we get to these equations,
It's still simple. All right. So here when we condense, so condense is going the other way. So instead of it being my constant, it's going to become my power. So we have log base 2, 3 squared. And what does that equal? Log base 2, 9. The constant becomes the power of the x. How do you feel about property 5? I do too. All right, let's put all our skills together. So we want to condense these down to single logarithms. So condensing them down, we're going to use our properties. Okay? We're going to always start with, you should always check for property 5. So we're going to start with property 5, which is where we are using our power rule. So notice here how I have 3 and 6. So using property 5, they're now going to become powers. So we have log base b q to the third plus log base b v to the 6th. Okay, now we're going to check for either property 4 or 3 can be used. In this case, which one are we using? We're going to use property 3. And the reason why we're using property 3 is because of the addition symbol. So we're going to use the product rule. If I am adding 2 logs with the same base, that means I'm multiplying their x values, right? So their bases are the same. So using property 3, I have log base b q to the third times v to the 6th. And then your last step is to check, can you use properties 1 or 2? No, there is no other b's that I can utilize.
so we want to make sure we go through all the properties before we just go to one answer.
Mm-hmm.
Does the answer matter now? That's
Yeah.
okay.
So I've condensed it down to 1 log. All right, number 2. Again, we're going to go through the same steps. So I'm going to start with property 5, turn my constants into coefficients, then my coefficients into powers. I don't know what I just said. So that gives me log x to the 4 minus log x plus 2 to the 6. And then I'm going to divide because of what? subtraction sign. So I'm going to have to use property 4. So that gives me log, and division matters. Your first term, that's your numerator. The second term is your denominator. So x over 4, x to the 4 over x plus 2 to the 6. And then can I use property 1 or property 2? No, there's no canceling out, no inverses being utilized. So this would be my final answer. We're going to start solving on Friday. Yeah. Right now, we just got to make sure we can condense, expand, simplify. Okay. All right. Good. Okay. Last piece of the notes is change of base. Okay. So you have seen logarithms with many bases. So the log key on the calculator usually only finds your common log, your log base 10. And so if you're using any scientific calculator, typically you will have to convert using the change of base formula. So our change of base formula is C stands for common log. So C is typically just 10 in most cases. But it's the log of M divided by the log of your B. Okay, and C, we typically just let C equal 10, and we use the common log that is provided. Okay, so here, change of base formula, we have log base 3 of 91. Well, in the most standard calculator, I cannot pull up log base 391. So as you can see here on a standard calculator, I just have log, right? I just have the common log. So if I wanted to find the log of what we have here, I'm going to convert this into common log base. So in this case, again, we let C equal 10. 91, so I have log of 91 divided by log of 3. And this is what I would put in the calculator to get an approximate value of what this would be. So in my scientific, I can type in log 91 log, and that's my first one, divided by 3 log, and it gives me an approximate value of 106. 4 and 106 6 thousandths. Was change of base terrible? Not at all, right? So for this one, again, use change of base formula. So change of base formula is saying, you're asking yourself 2 to the what power makes 81. So we're going to have 81. We have log of 81 over log of 2. We're going to use our standard scientific calculator. And I type 81, hit log. Uh-oh, I hit 4. I didn't mean to do that. 81 log divided by 2 log, and I get 301 thousandths, approximately. So my answer is approximately 301 thousandths. All right, change of base. How do we feel? Good? Doable? Oh. All right, so your homework, You have these 8 problems. We're a little ahead of, this was a lot smoother than I thought. So we only need 1 day of it. Yes. So for your homework, you're going to go through and write the expressions as a single log. We have expanding the expressions. And we have change of base.
And we got the homework on how to the notes.
Huh?
The homework on how to the notes.
Yeah. And then I think it's the same. It should be the same problem.
Yeah, right.
They are. All right.